Good afternoon. My name is Victor Martinez, and I come from the University of the Balearic Islands in Mallorca. Today, I'm here to present together with my colleague Per Antoni Bipiloni our new solar cooker design. Our collector comprises two reflectors, a flat heliostat and a stationary reflector. The heliostat employs the same tracking principles as the Schaeffler reflector. It has an automatic tracking axis, you can see here. This axis is operating at constant speed to adjust the mirror's positions throughout the day. Meanwhile, a second axis accommodates the sun declination and only needs manual adjustment every day or two, and this is this second axis. Most of you are already familiar with the tracking concept we use, as it is the same as the one employed for the Schaeffler reflector. Here you can see two ray tracing sequences demonstrating the tracking behavior during the winter and summer solstices. I would like to highlight three crucial aspects of our design. Firstly, the aperture area of the collector. The aperture area of the collector is entirely defined by the projection of the stationary reflector in the direction of the incoming sunlight. And since the sunlight consistently reaches the reflector from the same direction, the projected area remains constant, and so does the amount of energy that can be collected. Secondly, a noteworthy observation is that the entire heliostat isn't constantly used throughout the year. In fact, for the shown configuration, the whole mirror is only used during the summer solstice, as you can see in this figure over there, here. At any other time of the year, only a smaller section is in use, reaching a minimum during the winter solstice, as you can see, for example, in this figure. One might suggest resizing the mirrors to capture more energy in winter. However, this would necessitate an oversized concentrator, which is challenging to produce, and hence we opted for a design with constant energy output, acknowledging that parts of the heliostat would remain unused during the winter. Finally, the third thing I would like to point is that it's important to understand the stationary nature of the setup. The position of the structural elements, the reflector and the focus, remains fixed throughout the year, oriented south in the northern hemisphere and north in the southern hemisphere. This stationary design offers significant advantages for permanent facilities, as the only moving component is the heliostat. Now let's summarize the main features of our collector. It offers a simple equatorial tracking mechanism without requiring a variable geometry concentrator. The primary structural component remains fixed, making the flat mirror the only moving part. And these factors contribute to a consistent power output that depends solely on the direct normal irradiance, not the sun's position. And also this consistency extends to the radiation incidence angles on the focus. Unfortunately, in light nothing comes for free, and these benefits come at the cost of requiring a larger reflecting surface for a given aperture and demanding precise assembly for all the components to work properly together. In the implementation of our concept, we prioritized accuracy while also avoiding the need for complex manufacturing methods or advanced machinery. To this end, we utilize precise but readily available technologies like 3D printers. Our strategy consisted in constructing the reflector shape from basic tiles, so that thanks to the unique geometry of each tile, when assembled, they collectively form the required shape of the assembly, without requiring any special molds or features, as you can see in the final shape of the reflector made of these parts and connected with those small plugs. An important point to highlight is that we decided to approximate the parabolic shape using flat pieces. This approach not only simplifies manufacturing, but also results in a more uniform energy profile at the receiver, thereby mitigating the high peaks often associated with parabolic reflectors, which is a significant advantage, we think, for cooking applications. Unfortunately, we face size limitations with our current 3D printer, which resulted in a cooker in the end that it's smaller than what we consider ideal for serious cooking applications. It has an effective aperture area slightly less than a half square meter. We ordered a larger 3D printer more than a year ago, but it has yet to be delivered due to this the supply shortages you all heard about. Next, we had to choose the exact shape of the concentrator. While in all the other slides we presented off-axis designs, of course this is not the only option. A standard axis aligned design is perfectly feasible, as you can see in the figure on the left. Now you might be wondering, why did we opt for an off-axis design? We favor off-axis design primarily because it allows the aperture of the collector to remain unobstructed, regardless of what is placed at the focal point. And even in winter, when the sun rays are at their lowest angle, as demonstrated in this picture here, our design ensures that incoming radiation remains unimpeded. This versatility allows us to use various items at the focus point, from a single cooking pan to an isolated furnace, or any other device you would like to use there, without disrupting the concentrator's operation. Here you can see the prototype we've constructed. You'll notice the feasibility of placing the table beneath the structure without causing any interference, as the sun rays originate from above or from the sides, depending on the hour you use the cooker. For example, here in the image in the left, you see how we are using a pot directly exposed to the sun rays in the focus. And in the right side figure, we have a box oven, cork isolated cork box oven. While our primary motivation for choosing an off-axis design was to eliminate interference, it also affords us an additional benefit, which is that it allows for the construction of a simple triangulated structure to support the heliostat. In contrast with a standard parabolic concentrator, realizing this configuration would pose more difficulty, as the heliostat rotation axis would physically interfere with the cooking area, as you can see here in the figure on the left. For our reflector, we choose solar-grade aluminum sheets sourced from Alcan. Despite these materials' reflectivity values not being as impressive as some other alternatives, our experience has shown it has an excellent long-term performance under outdoor conditions. To cut the sheets, we used a CNC router. And also we did explore the possibility of using plastic foils like the ones previously sold by Reflectech. However, aside from potential durability issues, we were unable to achieve as a fine surface finish as we had with the aluminum sheet. And this is probably due to the minor irregularities we had on the 3D printer surface, 3D printed surface, sorry. Lastly, our tracking mechanism employs a stepper motor controlled by an economical Arduino board. Apart from the stepper and the piece of lead screw, both inexpensive and common 3D printer components, the remainder of the gearbox is also designed to be printed on a hobbyist-grade 3D printer. And we are currently exploring the possibility of using even cheaper mechanical devices such as mechanical timer switches used in conventional ovens. And we are confident that they could offer adequate precision for effective tracking. And well, now I turn the presentation over to my colleague, Per Antoni, who will elaborate on the testing performed on our collector.
The image on the left shows the deviation of the prototype parabola in relation to the CAD model in degrees, and the image on the right shows the distance of each point from its ideal position. The red colors shows the larger deviations and the blue colors show the points that are closer to the ideal position. Therefore, part of the beams projected by the parabola will be deviating from their ideal position, causing that the focus not to have the expected position. This check is very useful when identifying which are the design variables that are introducing more error to the system in order to correct them in the final model. In order to study the quality of the focus actually achieved with the prototype, an experiment was carried out which consisted of photographing the focus on a Lambertian surface and also photographing an incident radiation sensor in the same position. With the analysis of the images, it has been possible to determine that, given the direct irradiation of 705 watts per square meter that was available at the time of the test, in a circle of 220 millimeters in diameter, we reach 144 watts. After calculations, this results in an intercept factor of over 70%, indicating that the geometry is correct, but there is still room for improvement.
Once the prototype was built, it was possible to carry out the first experiments to determine its cooking power. The experiments have been performed under the environmental conditions specified in the American Society of Agricultural Engineering standard. Two different receiver configurations have been studied. The first one has a small concentrator in the part immediately below the base of the pot, and above it's covered by a thick glass lid. In the second case, there is also a third concentrator in the lower part, where it's the tube that directs the beams toward the base of the pot. In addition, the pot is encapsulated in a 4 mm thick cork box. Thus, the area for the third test is bigger to the additional intercept area that the glass lid adds. For both situations, the mass of water has been kept at 1.9 kilograms. Once the experiment has been carried out, the standardized cooking power has been calculated for an irradiation of 700 watts per square meter. But in addition, the methodology suggested by Ruivo et al. Has been followed, where it's indicated that the temperature difference between the environment and the load must also be corrected by irradiation value, in this case 700 watts per square meter. These values of power when the temperature difference between the environment and the load are 50 degrees can be seen in the table. Due to the bad weather conditions that we had in the last months in Palma de Mallorca, very few of the experiments performed have been complied with the environmental conditions set. In fact, in these cases presented, although these conditions were satisfied, it can be observed that the difference between total and direct irradiation is very large. In fact, the solar cooker being tested only takes into account direct solar radiation, so that power values using the total irradiation are not representative. For this reason, the results are also presented making the correction with the direct irradiation.
Using the same data, the cooker-octothermal ratio of the two configurations was calculated. Again, at the table we present both total and direct solar radiance that we used for the calculations. These two graphics show the linear curve used to obtain the core value when taking only into account direct solar irradiation. In absence of further experiments, the following conclusions have been drawn. Although the power obtained with the glass lid is higher, it can be observed how the cooker-octothermal ratio of the second configuration is much higher. This is largely due to the fact that the heat losses are much lower using the core box. Because the final prototype will have a larger interception area, it is expected that the cooking power will increase while keeping convection losses low.
As we wrap up our presentation, let's recap some of the key points we've discussed. Firstly, we introduce you to a novel solar concentrator design with an automated equatorial tracking specifically tailored for cooking applications. The flexibility of our design, especially regarding the receiver part of the cooker, opens up exciting opportunities. We've taken our concept from theory to practice, having successfully built and tested a functional prototype. Our tests have been encouraging, validating the geometry of our design, and we've also already identified areas for improvement. Despite the small size of our prototype solar cooker, the thermal results we've observed are also promising. And we believe that with continued refinement, our concept holds significant potential, and it could prove especially advantageous in contexts requiring automated tracking and permanent installations. Our journey so far has been exciting, and we are looking forward to the next steps. Thank you very much for your attention, and now we will be glad to hear for your comments and your suggestions.